Welcome to this lecture on electric charges and fields. This chapter introduces the fundamental concepts of electric charge, Coulomb's law, electric fields, and dipoles. And all of these are foundational ideas in understanding electricity and magnetism. So let's get started. We'll first talk about the two most important properties of electric charge, which is quantization and conservation. Now, quantization of charge means it comes in discrete amounts. All charges in nature are multiples of the charge of the electron. It's important to know the charge of the electron. It is 1.6 times 10 to the power negative 19 Coulomb. Now, essentially, charging a particle can be done either by friction, which is rubbing one material with another, by conduction, which is by touching a charged material with an uncharged one, or by induction, where you bring a charged object near an uncharged one. So these are the three methods of charging objects: friction, conduction, and induction. In all of these cases, charging involves adding or removing electrons from the object. Always remember, it's only the electrons that can be transferred. So when we say that an object is positively charged, that means it loses electrons. And if it is negatively charged, it gains electrons. And therefore, it's easy to understand that charging must be in multiples of the electronic charge. Because if you remove one electron, the object is charged by the charge of the electron. If you remove two electrons, then it gets double the charge of the electron, and so on. So here is an example. Question says, how many electrons are there in a charge of negative 3.2 times 10 to the negative 19 Coulomb? First of all, it is negative. That means electrons have been added. And the formula that we use comes from the quantization of charge. And that formula there is Q is equal to NE. Sometimes we add plus or minus to show that it could be positively charged or negatively charged. Now, from this formula, when you rearrange, you get N is Q over E. Q is given, that's the charge, divided by the charge of the electron, and we understand that two electrons have been added. So when it says how many electrons are there, it should be two electrons. The second is conservation of charge. Now, conservation of charge just means that the total charge remains unchanged. The total charge is constant. Or we could say that charges can neither be created nor destroyed. You can only transfer charges from one object to another. Now, as shown in this diagram, when amber is rubbed with a piece of cloth, you can see that before rubbing, they're both neutral. So you see that there's +2 here, -2, so it's neutral, +3 and -3. In nature, most of the atoms are neutral because the number of protons is exactly equal to the number of electrons. That is why they are neutral. And you must know that a proton has the same charge as the electron, only that it is positive. But when you rub it, coming back to this, when you rub the amber with this piece of cloth, some of the electrons are transferred. As you can see, amber has gained 2 electrons, while the piece of cloth has lost it. So that's why we say that charges are conserved. The total amount of charge taking the whole system is still the same. Now, based on electrical conductivity, there are 3 types of materials. They are conductors, insulators, and semiconductors. Now, semiconductors is a completely different chapter, and we will talk about that later on. But now we're going to look at conductors and insulators. Of course, conductors have a lot of free electrons, and metals are the best examples, and that's why they conduct electricity. While insulators, like rubber and wood, plastic, they have fixed electrons, so that means the electrons cannot flow, they are not free. So what is seen here is charging by induction. Let me explain that. So imagine that you have a neutral conducting sphere. This is shown in the diagram, it's a conductor. That means the charges are movable, but it's kept on an insulating platform. So you do not want it to be grounded. And you bring a positively charged glass rod near the sphere. Now, remember, I told you that it's only electrons that move. So what actually is happening is that the free electrons are moving forward. And that makes it appear as if this end is positively charged. Now, the phenomenon is clearly shown here in this diagram. So, number one, you bring a positively charged object near the uncharged one. The electrons move towards the positively charged object. Then you ground it. When you ground it, electrons from the ground come and replace this. So that part becomes almost neutral. Now, keeping the charged object there, you break the ground connection, and now the negative charge spreads out. So now you have a negative charge object starting with bringing a positively charged one close to it. So if you had brought a negatively charged object, you would have ended up with a positively charged object. Okay. Remember that in induction, you are not touching the objects, you're just bringing them close. Now, what would happen if you were to touch these two? Now, that would be charging by conduction. In that case, a part of the positive charge of this will be transferred to the uncharged sphere, which means both of them will be now positively charged. So, do you see the difference? In induction, you don't touch the object, you bring it very close. And not only that, after grounding, you made this have an opposite charge, which was negative, while you're bringing a positive charge. That's an induction. But in conduction, you touch them and both of them get charged, but the nature of charge will be the same. I hope that's clear. Here is an example. A metal sphere is grounded while a negative rod is brought near it. What is the final charge? So you are grounding it, and then while keeping it grounded, you are bringing a negative rod near it. What's going to happen? When you bring a negative rod near it, all the electrons are going to be pushed to this side, and the extra electrons will go to the ground. Therefore, the sphere becomes positively charged. Okay, because you were doing it while it was grounded. Now, second, why does a balloon stick to a wall after being rubbed? While you're rubbing it, it's getting charged by friction. So let's say it's losing electrons. So now the wall, the part of the wall where you rubbed, becomes negative, while the balloon has lost electrons and it is positive. And unlike charges, attract. That's why the balloon sticks to the wall. So that is charging by induction. Now, the most important law in electrostatics is called Coulomb's law. And according to Coulomb's law, the force between two charges, Q1 and Q2, depends on the product of their charges and also on the square of the distance between them. So the formula is written there, and I'll write it again. So this is Coulomb's law. F is equal to K Q1 times Q2 divided by R squared. Now, K is a constant, and this constant depends on the material in which these charges are placed. For air or free space, the constant is 8.99 times 10 to the power 9. And that's the unit, Newton meter square per Coulomb square. So notice that this is such a huge number, which means automatically if you had, let's say, a 1 Coulomb here and a 1 Coulomb separated by 1 meter. So you have two 1 Coulomb charges separated by 1 meter. The force between them would be that much. Wow. Showing that 1 Coulomb is a big unit of charge. Just because we say 1 doesn't mean that it's small. Here's another example. In this case, you have two charges. Notice it's 2.0 microcoulomb and negative 3.0 microcoulomb, and they are 0.5 meter apart. Find the force between them. Formula used. This is the formula, K times that. And when you work it out, you get 0.21576 newtons. And we know it's attractive because one is positive, the other is negative. If both were positive or both were negative, it would have been repulsion. There's another question again. Two electrons are 1 nanometer apart. What is the repulsive force between them? Nano is 10 to the negative 9. So be careful with that. See that? So when you work that out, you get 2.3 times 10 to the negative 10 Newton. So that is Coulomb's law. Now, electric field. Electric field is the space around a charge where its influence can be experienced. So if you have a positive or a negative charge, there is a space around it into which if you bring another charge, there's going to be a force. Technically, this space extends to infinity. But practically, because you have square of the distance in the denominator, the further you move away, the smaller the influence becomes. Now, to visualize the electric field, we draw electric lines. Now, these are called electric lines of force. And for an isolated positive charge, the electric lines go away from it. And the reason is we always take the standard as a +1 Coulomb. So if you keep a +1 Coulomb here, and this being positive, they're going to repel each other. So that's why the lines go away from a positive charge. But if it was a negative charge and you place a positive here, that's going to be attracted, right? So the positive charge is a standard. Whatever happens to the positive charge of 1 Coulomb is what determines the direction of the electric field. That is why the electric field is away from a positive charge and towards a negative charge. But if you have a positive and a negative kept together, as you can see at a small distance from each other, and by the way, that's called an electric dipole, and we'll look at that later. But then, this is how the pattern of the electric field would be. You can see that the electric line goes from a positive to the negative. Remember that all the time. And how do you know that it's going to be exactly this pattern? Now, that's again imagination. Remember that the standard is +1. So if you had kept a +1 coulomb somewhere here and it was free to move, then this is the path that it would have taken. So that's why electric lines are drawn like that, because it shows the path taken by a free 1 coulomb positive charge. Okay? So if you had a positive charge kept here, it would be repelled away along that line. So that's essentially the idea. But more important than that, if you wanted to find the electric field at any point, let's say if you wanted to find the electric field at this point, what you got to do is draw a tangent to that line and you would get the direction of the electric field. So if you wanted to find the direction of the electric field, let's say here, draw a tangent to the line of force at that point. See that? So that's another importance of drawing lines of force, because you know that if you draw a tangent to that line, at any point, you get the direction of the electric field. The fundamental definition of electric field is force per unit charge. Because remember, we started with 1 coulomb, whatever force acts on that 1 coulomb. So from there, you get the unit of electric field as Newton per coulomb. Later on, we'll see that there is another unit, but for now, the unit of electric field is Newton per coulomb. Okay, so here's a worked out example. A 2 microcoulomb charge is placed in an electric field of 3000 Newton per coulomb. What is the force on the charge? So you're given the value of the charge, you're given the value of the electric field. So you're given E and Q, and you're asked to find the force. Easy enough. Micro is 10 to the negative 6, and then you multiply them, you get the answer. A similar example here, what's the electric field? 0.2 meter away from a +5 microcoulomb point charge. Okay, it's a similar example, but the formula is different. Remember that at this formula, F is equal to K Q1 Q2 over R squared. Now, if you replace one of the charges with 1 coulomb +1, then F becomes E, because that's how we defined electric field. We defined that electric field is the force acting on a +1 coulomb due to this charge Q. So that's where you get that new formula for electric field, which is KQ by R squared. So if you're given R and you're given Q and you're asked to find the electric field, we just use that formula. E is equal to K Q over R squared, which is what is done here. You have K Q over R squared. So there are two formulas technically to calculate the electric field. Now, all of this I had, I think, mentioned. I'm not going to read all of them except this one. Denser lines indicate stronger field. That means if you draw more lines, if the lines are like crowded, then it's a stronger electric field. For example, if you look at this space, you have more lines. If you look at it further away in that same space, you'll have less number of lines, meaning the field is more stronger here than here. Also, electric field lines can never cross. Why? Because remember that if you draw a tangent at any point, it gives the direction of the electric field. If two lines were to cross, then you could draw two tangents at one point, which is impossible. You can't have the electric field along two directions at the same point. That's why electric lines never cross. Now, the example here we'd already done, draw the electric field for an isolated positive charge. That's the one, isolated positive charge. Okay. And then draw field lines for a positive and negative charge of equal magnitude. If you had a positive and negative, that's how it would be. Now, in real life, you rarely have isolated charges. What you're going to have is a continuous distribution of charge on objects. So in diagram A, you have a continuous and uniform distribution of charge on a rod. And in order to find the electric field at any point due to this rod, we have to define a quantity called lambda. This is called the linear density of charge. Now, linear density of charge is simply whatever is the total charge on the rod divided by its length. So lambda is just Q over the length. And so the unit of lambda is coulomb per meter. Okay, so that's lambda. But if the charge is spread out on a uniform flat plate, as shown here, all over its surface, then instead of defining linear density, we have to define surface density of charge, sigma. And sigma in this case is Q over the area, the surface area. Therefore, the unit becomes coulomb per meter square, coulomb per meter square for sigma. But what if the charge is distributed over a particular volume, as shown in figure C? Then it's going to be charge divided by volume. See how that is progressing? And the unit would surely be coulomb per meter cube. So you have three constants given here. Lambda is the charge per unit length. It's called linear charge density in coulomb per meter. Sigma, charge per unit area, also called surface charge density, and the unit is coulomb per meter squared, and rho is the charge per unit volume, and the units are coulomb per meter cube. Now, after having defined these three, we could find the electric field at any point P, for example, due to a thin sheet of chalk. So for that, we have to use calculus. We have to imagine that the surface is divided into small sections, as you can see. And then what is going to happen is each section is going to contribute, or the charge in that section is going to create an electric field at that point. And that electric field can be broken up into the X component and the Y component. And then similarly, the charge here is going to create an electric field in that direction. You break up that into its x and y, and you can see automatically that the x components cancel out and the y components add up. So that happens for every section, because for every section on this left side, you're going to have a symmetric section on the right side. And that's why we know that finally the electric field would be pointing that way. That's the net electric field. And after using integration, we can, or calculus generally, we can find the formulas. But there is a generalized the formula. There are formulas given down here. The electric field at any point P is 1 by 4 pi epsilon naught. Okay, that's the first time that's being introduced, so I need to write it. You see, the constant that we called K is actually 1 by 4 pi epsilon naught. Now, epsilon naught is 8.85 times 10 to the negative 12. Don't worry about the unit right now. Now, this is called the permittivity of free space. Permittivity. See, the word shows how much it permits the electric field to go through. So that is the permittivity of free space, vacuum, or air. All three have roughly the same, which is 8.85 times 10 to the negative 12. Now, if you put this in your calculator, if you put 1 over 4 pi times that number in your calculator, that's when you're going to get 8.99 times 10 to the power 9. Okay. So smaller the permittivity, bigger the value of K. Okay. So we're talking about air here. When it comes to other materials, we will see how its permittivity is calculated in relation to the permittivity of air. We can do that later, but I just want to tell you that instead of writing 1 over 4 pi epsilon naught, we could have just put the K there. So due to a point charge or due to point charges, so if you have a lot of point charges and you're trying to find the electric field somewhere, you have to individually find the electric field due to each point charge and then sum them up. Okay, so that's what this shows. The total electric field due to a lot of point charges is the summation of 1 to the nth charge of Qi by R squared. Yeah, where did we get that from? Remember, it's KQ over R squared for a single point charge. We took the K out and you have Q over R squared here, okay? Now, for a line charge, we have to use the calculus method and you will get 1 by 4 pi epsilon naught line integral of lambda dl by R squared. Lambda times dl by R squared. But if it's a surface charge, then sigma dA. You see the correlation there? And this shows the unit vector, which gives the direction of the electric field. Because the electric field is a vector. Now, again, for volume charge, it's a rho dV by R squared. Okay, so that is what is done when charges are actually distributed uniformly on objects. Now calculate the magnitude and direction of the electric field 2.0 meter from a long wire that is charged uniformly at lambda 4.0 times 10 to the negative 6 coulomb per meter. Now, what's important is to note that this is a long wire. That means it's infinitely long. And after integrating the expression that we had on the other page, which is this one, and applying the limit that the length tends to infinity, then you get this formula. So I'm not going to take the time to do all the calculus here because that's going to take a couple more hours. So you have to remember this formula and remember that it's applicable when a long wire means infinitely long is uniformly charged. So that will be the formula there. And since intensity is a vector, I'm going to put that. And you see that it's lambda by 2 pi epsilon naught r. Now, all of those terms are given. That's epsilon naught, as you can see. And the radius or the distance in this case is 2.0, and you get the electric field. And we know that if the wire is positively charged, so if the wire was here and the point was here, it's going to be radially outward. If it is negatively charged, and then the field was going to be radially inward. Okay, here's the second question. A spherical water droplet of radius 25 micrometer. It's really small. It's a droplet. Carries an excess of 250 electrons. What vertical electric field is needed to balance the gravitational force on the droplet at the surface of the Earth? So you have a droplet and the gravitational force is acting down on it. That's given by mg. And we're trying to find out what the electric field should be so that the force acting, which would be QE, right? Force is QE, balances the weight. So already from the diagram, you understand that QE must be equal to mg. Now, mass is volume times density, so that's what is given here. So first, being a sphere, this is the volume of a sphere. And once you get the volume, you multiply it with the density of water, which is 1,000, to get the mass. And then you know that the weight is mg. And since the charge is given, it's 250 electrons. So the total charge is 250 times the charge of one electron. So we got it. Now set them equal to each other. So the electric force is equal to the gravitational force. And then from there, you can calculate the electric field required to balance the weight of the drop. Here's another one. The charge per unit length on the thin semicircular wire shown below is lambda. What's the electric field at the point P? So the difference here is that it's not a straight conductor, but it's semicircular. In this case, the idea will be the same, except that we'll be bringing a small angle d theta. So if you take this small segment here, it's going to subtend that angle d theta there. So that's d theta. And then we can use integration to go all the way from this angle to the other, which you know is 180 degrees or pi. See, that's the idea. But we're not doing the entire process. I'm just giving you the idea there. And then again, as we saw before, we know that at each point it'll be along that, and you can break it into x and y. The x's will cancel out, okay? So that's what we're doing. Um, the electric field due to a small charge is that. We have seen that. And then decompose the vector into its components. We only take the vertical component, which is going to be sine theta, and then integrate after that. Once you integrate, you get lambda by 2 pi epsilon naught. Okay, so that's the answer, lambda by 2 pi epsilon naught r. Okay, there you go. So what do you notice? You notice that whether it was a straight conductor or semicircular, the formula stays the same. That was the purpose of giving you this exercise. So if ever that question is asked, are you using the same formula? All right. In nature, charges always exist in pairs. If you have a positive charge, you have a negative charge. And that's called an electric dipole. Basically, an electric dipole is two equal and opposite charges separated by a small distance. And we have to define what is called the dipole moment. It's a vector. So dipole moment P is one of the charges times the distance between them, QD. And it's always from the negative to the positive. So if you have a positive charge here and a negative charge here, both Q, then let me use that. Okay, then the electric dipole moment is that way, always from the negative to the positive. And obviously, D is the distance between the two charges. So we're going to see what happens when an electric dipole is placed in an electric field. I have a diagram here. Down below, you can see that it's a constant electric field. How do you know it's a constant electric field? Do you see that the distance between the lines is the same? That means it represents a uniform electric field. So at whatever point you measure the electric field, it's going to be the same. In such an electric field, you have placed a dipole. You can see the dipole here. And what's going to happen is, by definition, we know that the electric field represents the force acting on a positive 1 coulomb, right? Therefore, due to the field, there will be a force on this positive charge in that same direction, but there will be an equal force on the negative charge in the opposite direction. And that creates a torque. I hope you remember torque. How is it defined? It's a vector. Torque is the cross product of the distance and the force. So in this case, in order to find the torque, what you got to do is you have to remember that we're taking the distance between the two forces. So you can see that this is the line of action of that force. This is the line of action of that. This is the perpendicular distance between them. So you'll see a little triangle coming up there, and this angle is going to be relevant. So to calculate the torque, you're going to go, if d is the distance, from this right angle triangle, you know that sine theta, let's see, sine theta is opposite. So this distance, which we call r, sine theta is r over d. So r is d sine theta. Therefore, when you plug it back into this formula, torque is going to be d sine theta times f. Do you see that? So it's going to be d sine theta times f. Okay. Now, remember that dipole moment is defined as charge times this. Okay. And also, okay, let me substitute d sine theta. What's f? F is q times e. Is it not? F is q times e. So now if you take d and q and multiply them, you're going to get the dipole moment P. Therefore, this can be written as P E sine theta. All I did is I combined the product D into Q and called it the dipole moment. Now that's a vector. This is a vector. This is also a vector. So by definition now, torque is the cross product of P and E, because cross product of two vectors means those two vectors multiplied by sine of the angle between them. Okay, so see sine of the angle coming there in between them. So that's the formula to calculate the torque. So there is an example here, worked out example. A dipole is kept in a field, so that's the electric field, and makes an angle of 30 degrees with the field. That's theta. And P is given. Look at the unit. That's not centimeter, that's coulomb meter. And torque is just PE sine theta. So multiply the dipole moment with the electric field sine of the angle, and you get the number. The last topic in this chapter is calculating the work done in rotating a dipole which is situated in an electric field. So let us consider that initially the dipole is making an angle theta 1 with the field, and then from there it's rotated to another angle theta 2. Work done is given by integral tau d theta, because it's rotation. Instead of force times displacement, which is in linear motion, we have torque multiplied by the angle in rotational motion. Now, since we know that the torque is P sine theta, substitute that. And when you integrate, the constants are taken out, P and E are taken out. And after integrating, you get negative cosine theta. And then when you substitute the limits, you get negative PE cosine theta 2 minus cosine theta 1. So that's the formula for work done in rotating a dipole. Now, from this formula, we can define the potential energy at any angle theta as minus PE cosine theta, just from this formula. So that is what you use when you calculate the potential energy at any angle theta. Now, of course, this means that if the angle theta is 90 degrees, okay, so you have a situation, let me try to draw it quickly. So you have a situation where the electric field is that way, and you have the dipole situated this way. So that's the negative charge. This is the positive charge, which means the dipole is making 90 degrees with the electric field. In this case, we know cosine of 90 is 0. That means the potential energy is 0. So the zero potential energy is when the dipole is making 90 degrees with the electric field. What about if it's making an angle of 0 degrees? That means it's aligned with the field. It's in the same direction as the field. Then you're going to get cosine 0 as 1. So that would be the minimum potential energy, which would be negative PE. On the other hand, if the dipole is situated with a negative here, the positive here, so which means its dipole moment being from negative to positive is exactly opposite to the electric field, then you're going to get maximum potential energy, which would be plus PE. That's because cosine of 180 degrees is negative 1, and two negatives make a positive, okay? So that is this chapter. So in this chapter, we looked at a lot of concepts, and all of this is important in understanding electrical circuits when we get there. So these are just conceptual chapters. You have one more, the next one, where we talk about electric potential, which is going to be conceptual. But it's important to understand all these definitions and concepts so that you're able to deal with electrical circuits in a confident manner. Thank you and see you on the next one.